now we have another circuit element called the inductor. So inductor, what it basically does is it opposes the change in current through it. So it and the voltage, the reverse voltage which an inductor applies is given by this equation L di by dt, where L is the inductance of the inductor. And similar to capacitor, this also stores energy in it, and the expression for energy stored in an inductor is half Li squared, where I is a current flow. And so you must be wondering how this inductor stores the energy. So it stores in form of the magnetic field. So whenever you have like a wounded wire like this, it can act as an inductor, and the magnetic field which it produces whenever a current flows through it is given by this equation. So mu naught mu r Ni by L, where N is the number of turns in the wound made the wire. So yeah, and in the inductance of that solenoid is given by N phi by I, where phi is the magnetic flux and N is the number of turns and I is the current through it. So yeah, basically it all depends only on the geometry of the wire, so not exactly on the current, the flux which actually passes through it. So yeah, this is what is the inductance. And now we have another device called a toroid, where the an inductor is like you basically make the inductor into a circular shape and then pass current through it and find the inductance. So here, when you do the same thing, you get the inductance of the toroid as mu n square a by 2 pi r, whereas the radius of the toroid. Now, similar to the Wheatstone bridge, we have something called an AC bridge. So here we look at reactance. So reactance is nothing but the circuit elements like capacitor and inductors, what they like offer as resistance to time varying voltage fields. So when you apply AC voltage, these also like produce some kind of resistance. So this is called as reactance. And when you derive the expressions, what you get is L4 by R2 C1 R2. So it's nothing but similar to the Wheatstone bridge, where like L4 by R3, you divide this by this, which is equal to R2 by C. R2 by C. Now, let's go to part 3. So here we study like, impedance transforms, where like, we actually calculate what the reactance of capacitors and inductors are. So here we use Laplace transforms to like move from the time domain to the frequency domain, where if you Laplace transform R, you get R exactly, but you transform the capacitor's reactance, so you get 1 over SC, and then the inductor's reactance will have to SL. So if you do the Laplace transform, you get this as the frequency domain. So yeah. So when you have transformed everything into the frequency domain, you can like analyze the circuits exactly like the resistors when you had it in the time domain. So yeah, instead of R's, you'll have Z's. By Z's, we need impedances of the all the components, be it capacitors or inductors or resistors. So similar to the series and parallel expressions, we also have this similar expressions for all these impedances. So yeah, similar stuff. So we have voltage divider and the current divider rules for all these things. Now coming to low pass filters. Yeah. So now coming to the next concept, which is the low pass filter. So here we have a circuit which acts in such a way that it only allows low frequencies to pass through it. So if you apply some voltage, say VI here, so what happens is if only the low frequency component of this VI will make it to the output voltage. So yeah, so analyze this to analyze the circuit, we can use the time domain to frequency domain transforms, which we learned earlier. So like replace the impedance of the capacitor by 1 over SC, and then yeah, analyze the circuit. So yeah, so using voltage divider rule, we get this expression, and then we define something as a transfer function. So this transfer function is nothing but the output voltage divided by the input voltage. So when you calculate this, you get something like 1 by 1 plus S by omega naught. So where omega naught is we define it as 1 by RC, which is the frequency, cutoff frequency. So yeah, for S, if you actually like S, you can substitute S as j omega. So if you do that, you get 1 by 1 plus j into omega by omega naught. And then the magnitude of the transfer function can be calculated as follows. So this magnitude of the transfer function can be used to calculate the gain of the signal. And we also define something as 3 dB frequency. So this is called as a corner frequency also. Like as I told you, this omega naught. So this is 1 by RC. So this is a very important frequency. It's called as a 3 dB frequency. Why is it called 3 dB frequency? We'll see here. So because we define gain as 20 log magnitude of transfunction. So when we do this, when we have omega by omega naught equal to 1, or in other words, like when omega equal to omega naught, you get the gain as 3 decibels. So that is the reason why you call omega naught as the minus 3 dB frequency. So yeah, it is also called as a corner frequency. Yes. So now we can draw a response curve. So this is called as a frequency response curve, where we vary the frequency of the input signal and see how the gain of the circuit varies. So here what we see is for the low frequencies we have like zero gain. Like see by zero gain I mean like Vi will be equal to Vo. So there's no attenuation of the signal. But as you increase the frequency to higher numbers like 100, 10, so what happens is the circuit doesn't allow this high frequency. So yeah, the output signal will fall to zero. Yeah, so for this reason, the above circuit which we saw is called as a low pass filter. Now, similarly, we have something called a high pass filter, which can be constructed using inductors. So when you use inductors, like you have to do similar circuit analysis. You convert the original circuit into time, or the time domain circuit into the frequency domain, and then you replace s by j omega, and then you get the transfer function, and then you can plot the frequency response of the circuit by taking 20 log of the magnitude of transfer function. So when you do this, you get the exact opposite thing of what we got for the previous circuit. So here what happens is for the low frequencies, the gain is very less, which means that the output voltage is negligible for low frequencies. But as you keep on increasing the frequency in this interval, you get to see whatever is in the input signal. So Vi equal to Vo at this region of the curve. So that is the reason this is called as high pass filter. So yeah, that is about low and high pass filters. Okay, so now moving on to the phase plots. So we learned that how to plot the frequency response curves for the circuits. Now let us learn how to plot the phase plots of low pass and high pass filter. So like here by phase plot we mean like how does the phase of the output signal change with respect to the phase of the input signal. So yeah, for a low pass filter at low frequencies, so you get the phase difference of between output and input as zero. But then as you keep on increasing the frequency, you can see a phase shift of minus 45 degrees. Now, okay, now we've learned how to construct a low pass and a high pass filter. So what someone naturally would do is go on and construct a circuit which can like pick a frequency, not just some threshold, not just frequencies after some threshold, but to cherry pick a single frequency, we can like include both the components in a single circuit and call it a resonator circuit. So what this resonator circuit does is it just peaks out around the required frequency, and it gives zero output for all the other frequencies. So this is what you use for any like radio frequency applications like radio, FM, such stuff. They use a circuit to pick any one frequency band which you can listen to. So yeah, when you convert this into the frequency domain, you get the circuit, and you calculate the impedance by input impedance by dividing the input voltage by the input current. Now here, this will be a second order system of differential equations, which will be very hard to solve if you did not convert it into the frequency domain. But luckily for us, we have the Laplace transform, so we can analyze the circuit in a linear fashion, and we can calculate the impedance of the circuit. So the impedance of the circuit can be given as R plus J into omega L minus 1 by omega C. And then, yeah, you just calculate the magnitude of the impedance, that is the uh, resistance of the circuit, and then the conductance is nothing but the inverse of the resistance. So now I told you how it fixes a certain frequency, right? So let us see what happens at a selected frequency omega. So when omega will be equal to omega naught, this term omega L and 1 by omega C, they cancel out, and then the resistance only becomes R. So that is when the resistance of the entire circuit becomes very low, and the voltage becomes very high. So yeah, that is how a resonator circuit works. So here you can see.